Welcome back. In this video, we're going to be looking at Chapter 6, where we've moved up one more layer in the OSI model, now talking about Layer 3, which is the network layer of the OSI model. This is where we start to introduce IP, the Internet Protocol, which is probably the most widely used Layer 3 protocol in existence today because it was developed for use on the Internet. And as pretty much everyone wants to connect their networks to the Internet today, they are all interested in running the IP, Internet Protocol. So if we take a look at IP, the Internet Protocol, it was really designed to be a slim protocol that only did what was essential for getting data from one location to another location. As a result, there's three big characteristics to IP. One is that it is connectionless. So what we mean by connectionless is that there's no connection made with the destination before we start sending traffic. If you think about like a telephone call where you pick up the phone and you get a dial tone and then you dial a phone number, as soon as you dial that phone number and the other end picks up, you now have a connection. And any traffic that you put in, aka your voice, will pop out on the other end. So you have this kind of like ongoing connection until you hang up. Right? IP doesn't work that way. It doesn't establish any kind of connection before it starts sending traffic. IP, you just start dropping traffic in with a destination address. It's more like putting a letter in the mail. You put it in and you just wait for it to get to the other end. There's no connection established in advance. The next thing that is true with IP is that it is a best effort protocol. That means that it is inherently unreliable. There's no guarantee that traffic gets to the other end. So again, similar to dropping a letter in the mail, you just drop it in and hope it gets to the other end. You're relying on your application or something at a layer higher than layer 3 to determine if the traffic got to the other end. Now, we'll talk about some things once we get into layers 4 and above about ways that some applications can in fact verify traffic got to the other end, but it's not part of the IP protocol. That's part of something that's happening up above this. It's not built into IP. And then the third thing about IP is that it's media independent. Now today, it seems like you wouldn't come up with a networking protocol for general purpose use that was media dependent. But before IP came out, there were a bunch of layer 3 networking protocols that actually said, okay, this networking protocol can only run over unshielded twisted pair or can only run over coax. Even though it's a layer 3 protocol, it has to work over certain types of network media. But when they designed IP, they knew we want this to be able to run over lots of different types of media. So you can run IP on unshielded twisted pair, on coax, on fiber, and even a bunch of different layer 2 protocols as well. It doesn't have to run on top of Ethernet. You can have point-to-point protocol or a bunch of other things. So even if you're on a dial-up modem that's not using Ethernet, you can still run IP. So those are some of the three big characteristics of the IP protocol: that it's connectionless, that it's best effort, and that it is media independent. Now, at the beginning, we of each packet, right? Each IP packet has a header on the front. Now, we're not talking about our frames anymore. We're talking about this is all inside of the data portion of the layer 2 frame. But at layer 3, we have a packet, and that packet has a header on the front. This is where all the address information is, and there's a bunch of other stuff in here. So the IPv4 packet header is 20 bytes long. And this is kind of showing you how that information is divided. The first byte of information, okay, tells us the version. That's actually the first half of the first byte. It takes 4 bits to have a version number. So when they created this, they knew we might have more newer versions of IP that get released out. And we may want to change the rest of this stuff. In a little while, we'll see that they did in fact do this when they came out with IP version 6. So when the packet arrives at a device, it needs to know where all these different bits of information are. And in order to do that, it needs to know what version of IP this packet is using. So for IP version 4, this version chunk of the header will always have this 4-bit value. It'll have 0100, which is 4 in binary. So that's what we've got here. You'll see we have a header length. We have some differentiated services, and that can include either a dynamic services control point or an ECN value for congestion notification. We have so this is the length of the header. This is the total length of the packet. So we have 2 bytes to say how long the packet is so that the receiving end knows how much data is going to be coming in the packet. We have some identification information, a space for some flags, which is just a way for programmers to say, hey, here's some information, like this feature is enabled or this feature is not enabled. This thing called a fragment offset, which we're not going to worry about. We're not going to worry about the header checksum either. Now, what you're going to find is that a bunch of these headers aren't actually normally used. They were things that the designers of IP thought were going to be useful, but turns out we don't really need them. And so when we came out with new versions of IP version 6, we came out with a much simplified header. But they all have to be there in every IP version 4 packet. The ones that are maybe the most important to us are that it's a version, the differentiated services section, the time to live value. Now, the time to live value is an 8-bit binary value, so 1 byte long. And when you send any IP packet, you set this to a number. A common number might be 30, or maybe 15. And what happens is every time that packet goes through a router, the router subtracts 1 from the time to live value, so that as the packet moves through the network, the time to live value keeps counting down every time it goes through a router. Once it gets to 0, if it happens at a router that the time to live value goes down to 0, then it will discard the packet. It'll trash the packet. It will not keep moving the packet through the network. So the reason for having this is in case we have a loop in our network where traffic keeps flowing back and forth between, like one router thinks it should send it to another router and that router thinks it should go back to the first router. If we have traffic moving back and forth forever, we don't want to have that circulating forever in our network, because over time we could have, packets that just don't have anywhere to go, and the network is confused about where to send them, and so it just keeps sending them back and forth. We don't want to have that happen forever and suck up all of our bandwidth with just these zombie packets floating around. So instead, what we have this time to live value, and when it gets to 0, it means it's gone through so many routers that the computer that originally sent it has said if it has to go through that many routers, it's probably not going where it needs to get. And so it can drop the packet. We also have a field called the protocol field, and that tells the device which is handling the packet something about the information inside the IP packet. What layer 4 protocol is existing inside the packet? So it helps prepare the device for if it needs to read or do anything with any of the layer 4 data, what type of layer 4 packet to include. So examples of that are going to be like TCP, Transmission Control Protocol, or UDP, User Datagram Protocol, are probably the 2 most common ones we might carry. We might also have like ICMP, the Internet control and messaging protocol, which is used for things like pings and so on. So this is telling us what information to expect inside the data portion of the packet, what's happening at layer 4. And then the next big thing that we want to pay attention to, source IP address. This is the computer or device that originated the packet, where it is originally from, and the destination IP address, where it is finally going to. Each of those addresses is 4 bytes long. 4 bytes is 32 bits. With IP version 4, the addresses are all 32 bits long. So that's what our IP version 4 header looks like. Now, there's some problems with IP version 4, right? There are about 4 billion total IP version 4 addresses, and that's because the addresses are 32 bits long. And there are you can count up to about 4 billion if you have 32 bits. So starting with 1, we can go up to, 4 billion. So that seems like a lot. But as we start to put our thermostats online and we start to put our phones online and we have more than one computer each, we start to end up very quickly where as the internet spreads across the world and continues to grow and spread, we have more than 4 billion devices that want to be on the internet. So we don't have enough addresses for them. Now we've come up with some clever things like network address translation, or NAT, which allow multiple devices to hide behind a single public IP address and use some private IP addresses. We'll be talking more about that as we go further into the course. But NAT does work, but it has some strong limitations to it. The other thing that's happening, in addition to the fact that we've run out of IP version 4 addresses and people still want to connect more stuff to the internet, is the routing tables on the internet, right? So if you're an internet service provider and you have a routing table on your router, you need to have a list of every possible network that traffic could go to, and then where the traffic needs to go if it comes to your router from one of your customers, where does it need to go next in order to get to that network? And because of the number of different networks and internet service providers on the internet, that routing table continues to grow. Now, there are things we can do called like route summarization to make that table smaller. In other words, if all of these networks are connected through this one ISP, we can just put one entry into our routing table for that internet service provider. But in order to do that, we have to have those networks all have to be sequential in number. And with IP version 4, there just wasn't a feasible way to have those networks be sequential in number. So the routing tables grow and grow and grow. And that makes routers slower and slower and slower. It requires routers that have more and more memory to handle the traffic on the internet. And so that's just not a feasible, we can't grow forever in that way. So that's another problem with IP version 4. And then, as we mentioned, we used network address translation as like this band-aid to allow us to connect more devices to the internet than we really have addresses for. And it lets us share a single public IP address, but because that address is shared, you don't have what we call end-to-end connectivity, meaning that I can't communicate directly from my PC behind my NAT router to your PC behind your NAT router. You have to do like port forwarding in your router. And that starts to add some complexity. NAT also does some nasty things to the IP version 4 header. It has to modify the header every time that it goes through a NAT device. It makes troubleshooting very hard. It's basically the bane of existence for network administrators. We want desperately to get rid of NAT. So that's one of the other major limitations with IP version 4. So troubleshooting is much harder as well. So what happened? Well, a number of years ago, and by number of years ago, I mean a number of years ago, more than 20 years ago, we already saw this problem coming as the network was growing and growing in size. So we created this thing called IP version 6. So IP version 4, as we said, has about 4 billion addresses. Well, We ran out of those between the time IP version 4 came out, and by the early 1990s, we knew we were going to run out of these already, right? So 30 years ago, we already knew we were going to run out of these. Now, what the Internet Engineering Task Force said is, okay, this is going to be painful. It's going to be painful to change from one version of IP to another version of IP. We do not want to have to do this again for a very, very, very long time, because IP version 4 only lasted like 20 or 30 years. Okay, we don't want to have to do this in our lifetime for sure. So instead of just making a few more IP addresses, we made a lot more IP addresses. So we went from 4 billion IP addresses to 340 undecillion IP addresses. Now, you've probably never even heard of an undecillion, right? So this is not the number of addresses. This is not one undecillion. This is the number of zeros after the 1, right? So this is a 1 followed by 36 zeros. That is a huge number, okay? We can think about this in some other ways. It's been speculated that we could provide an IPv6 address for every grain of sand on Earth. Okay, that is a huge number of IP addresses. Again, so with IPv6, we want to make sure that we have so many addresses available that it's basically impossible for us to run out until we expand to many, many more worlds than the Earth. Okay, so that's something that we want to keep in mind. The next thing is we learned some stuff about IP version 4. We learned we didn't need all of these header fields. There are some that are important and a lot that are just extra information, and those fields have to be carried in every IP packet that's flowing in the world. That means we want to send a nice small packet. We've got all this extra, like basically zeros that we need to send that slows down communication that we don't really need. So we've simplified the header, we've reduced the number of fields, and just kind of made it more of the essential information. Then, because we have so many IP addresses, we can get rid of NAT. Every computer, every device that's attached to the internet can have its own public IP version 6 address. Now, you can still use a firewall and block traffic from the internet into that device if you want. You can limit what ports traffic is allowed to flow on, so you don't lose any of the security benefit that people kind of accidentally got with NAT, but you can restrict the traffic just to particular devices rather than to an entire network. So we can get rid of NAT, and we can have public IP addresses for each device. It makes troubleshooting a lot easier. We don't have to play any games modifying the packet header as it flows through the network and so on. So much better situation all around. Now, if we take a look at the IP version 6 packet header, here's what it looks like. So we actually have doubled the size of the header. So it's now 40 bytes instead of 20 bytes. Now you say, wait a minute, I thought you said that we were going to reduce the fluff in the header, and the old header was only 20 bytes and it had all that fluff in it. Yes, that's true. But remember, those old IP addresses, the source and destination IP addresses, which we absolutely have to have, were only 32 bits for the source address and 32 bits for the destination address in IP version 4. With IP version 6, because we have 128 bits just for the source IP address and 128 bits just for the destination IP address, that means we can divide by 8, right, to get the number of bytes. So if we do that, we take our 128 bits divided by 8, we have 16 bytes. Oops. We have 16 bytes just for our source address and another 16 bytes just for our destination address. So just the IP addresses alone are going to be more than the 20 bytes total header size of IP version 4. So what we did, though, in order to keep the total size down to like 40 bytes, is we slimmed down the rest of the stuff in the header. We kept the version because we want to have that version number at the front so that we can have backwards compatibility. We have a traffic class that we can use for some quality of service stuff. We have a flow label so that we can tag traffic and handle different types of traffic differently. In large enterprise network, that is a useful thing that we want to do. We need to have some length so we know how long the next how long the data portion of the IP packet is. We need to have this next header, which is basically the same as the protocol field in the IP version 4. It tells the device that's processing this packet what type of header or what type of protocol is being carried inside this IP packet. And then the hop limit, which is basically the same thing as the time to live field that we had in the IP version 4 packet. So we have simplified the header a lot. We have doubled the size of the header, but that's kind of unavoidable given how much larger we have made the address space in IP version 6. Okay, so when your computer sends a packet to another host, if it's on the same network, it's going to send it directly, right? It's going to set the MAC address of the frame that's carrying that packet to what the destination MAC address of the device is. But if the packet needs to go to another network, your computer is going to send it to a router, right? And the way that it figures that out is your computer has a routing table, right? So you can actually see this on Windows. Every operating system has a way to do this, but on Windows, if you open up a command prompt and you type route print, bad keyboard, you can see your routing table. Now, this stuff down here is my IPv6 routing table. Let's just move up here and look at my IP version 4 for a minute. So this is the routing table on my computer. So these are all the different destination networks where traffic could go to from this computer. And then this is how the computer is going to reach each of those networks. So all these ones that say on link, that means this computer is directly connected to that network. And we can send information from this computer directly just using layer 2 to devices that have these IP addresses or belong to these networks. However, we have this special network up here, this network that says 0.0.0.0. We call that the default gateway, or we call that the default route. And the default route is for any network that's not in this list, it will use this network. If you look, that one, instead of saying on link, it has an address. It has a gateway address, and that is the default router. That is the router my computer will send the traffic to if it is going to this network, which is the network that represents all networks that are not specifically listed here in the list. So 172.20.5.1 is the address of the router on my network. So the traffic's going to arrive at that network or at that router, right? So it's going to arrive at router 1 here. That router needs to do something with that traffic. So what's that router going to do? Well, the router also has a routing table, and it looks in its routing table to determine where to route the packets. There are 3 different categories of routes that there might be in a router. One is directly connected routes. Those are just like the routes that my PC had. The router knows about every network that is plugged directly into the router. So if it's going to one of those networks, the router just knows, oh, I just need to send it out to its final destination on one of these networks that I am directly connected to. Now, obviously, with the internet, we can't possibly have your router at home, for example, can't be directly connected to every network on the internet. So we also are going to have remote routes. Remote routes are like, okay, we've got these networks over here, in this case 10.1.1.0 and 10.1.2.0. Router 2 is directly connected to those 2 networks, but router 1 is not. So router 1 might have a remote route to 10.1.1.0. So router 1 would say, oh, I know how to get to 10.1.1.0, but I'm not directly connected to it. What I need to do is send it to router 2. and I'm directly connected to the same network that router 2 is on. Okay, so router 1 could have an entry for 10.1.1.0, but it would just say, okay, to get to 10.1.1.0, I need to send the traffic to router 2. And the address for router 2 is 209.165.200.226. So that's the remote route. The third type of route is just like our computer has a default gateway, a router could, in its routing table, also have a default gateway. Because your typical router at a business or home doesn't need to even have a remote route for every network that's connected to the internet. It would take too much RAM and processing power on most people's routers. They just wouldn't be able to handle it. So on most small routers, like ones that an internet service provider is not running, you're probably going to have a few directly connected routes, maybe a few remote routes, but most of the time, if you're going out onto the internet, you're going to have a default route. And the default route is if the router doesn't have any other networks that are a better match for the traffic, the router will send it out of its default route to whatever the next router in line is. Okay, so those are the three main types of routes that the router might have to use to make a decision about where to send the traffic next. I should mention also, the other thing I wanted to remember to mention is that whatever the address is, so like router 1, if router 1 is sending traffic from a computer that's attached over here, PC, on the 192.168.10.0 network, the computer will send it to like 192.168.10.1. Then when it gets to the router will send the traffic, if it's trying to reach this 10.1.1.0 network, that it'll send it to router 2, right? The address it's going to use for router 2, because routers have more than one IP address. Your computer probably only has like one IP address if you only have one network card. But routers have more than one IP address. They're connected to multiple different networks. So router 1 has 192.168.10.1, 192.168.11.1, and 209.165.200.225. Router 2 also has 3 IP addresses. Each network that router 2 is connected to has a separate IP address. So what address does router 1 use in order to send that traffic from the PC over to 10.1.1.0? Well, the next address that router 1 uses is this one, 209.165.200.226, and we call that the next hop address, because router 1 can only send the traffic to a network that it is directly connected to. And the only network that it shares with router 2 is this one, 209.165.200.224. And its address is .225, router 2's address is .226, so the next hop address that the router 1 will use in order to reach the 10.1.1.0 network is 209.165.200.226. So if you see something that's talking about next hop addresses, that is what they mean. It's the address of the next router that the traffic will go through. Okay, now, if we look at a router, here's a picture of a router similar to the routers that we have in our lab. And this is a Cisco 1941. But most business class routers are going to look more or less something like this. So a few things to kind of note on the router, right? We have a power supply port here. We have console ports down here that you've connected to in the past, right? Those console ports are used for programming the router over a serial interface. Here, and there's a USB port here you can use for programming the router as well. That USB port is just a internally in the router, there's a USB to serial adapter that is just, it's the same thing as the other console port. They're both exactly the same. This one is just providing a USB interface that's converting that serial connection to a USB for you. But if you plug it into your computer, it's still going to show up as a serial port. Okay. You also may have seen above the console port, there's another port that's labeled AUX, the aux port or auxiliary port. What's going on with that? That's basically a second console port. You can actually use it for programming the router just like the console port, but what it was originally designed for is to attach a modem to. On some new routers, they don't have the aux ports anymore. They just have the console ports. It used to be that you could attach a modem to that aux port, and then you could have dial-up access to the router for programming purposes. So in case you erased the whole router and you couldn't access it over the network anymore, but it was at a remote location, you had a phone line going to it, you could dial into it and keep programming. This can be a security vulnerability because if you put a password on your console port, but you don't put a password on your aux port, if someone has physical access to the router, they can just you can plug a regular console cable into that aux port and open up TerraTerm or a terminal program and connect to the router exactly the same way that you would with the console port, but it has a separate password. So if you forget to set a password on the aux port, that's not necessarily a good thing. Over on the right side of the router, you'll see these two ports here. These are Ethernet ports. They're gigabit Ethernet or fast Ethernet ports, depending on your model of router. And so those are for connecting to Ethernet networks. So this router can connect to 2 Ethernet networks. Below one of those Ethernet ports, you'll see a couple of USB ports. These USB ports can be used for hooking up a flash drive for copying files on and off of the router, so you can actually save your configurations. You can back them up to a USB flash device, and then if you have to replace the router or something, you can reload the configuration onto the new router. On the left side of the router, a couple of things. On the bottom of the router, you're going to see these two slots. One might have a compact flash card in it. Compact flash is like something that you used to see in cameras for taking pictures a lot, but it's basically just flash memory storage. And that's basically the hard drive of the router. That's where your configuration files are stored. On the router, where the operating system of the router is stored is behind one of those little doors on a compact flash card. Up above the compact flash slots, you'll see that this router has some slots up here that are they're enhanced high-speed WAN interface cards. Now, in our routers in our lab, you'll see that the far right one of these has 2 ports on it that look like Ethernet ports, but the card is labeled T1 E1. Okay. This is where you'll oftentimes put cards for accessing wide area networks. So these 2 ports on the card in our lab routers are for connecting to wide area network connections, or in our case, for simulating wide area network connections. Routers themselves seem like mysterious advanced things. They're really just specialized computers. They have CPUs, they have memory, they have long-term storage, they have network interfaces, and they run an operating system just like your computer does. But instead of Windows or Linux or something like that, they run this Cisco iOS operating system. So they are really just specialized computers. In fact, you can use a computer as a router. You can take a computer, and if you put the right type of operating system on it, for example, if you're using Linux or BSD, it's pretty easy to do this. But you can convert that router, or convert that computer, if it has multiple network interface cards in it, into a router that can route traffic from one network to another network. Now we're going to get started learning to do a little bit of configuration on the routers. So just like we did in a previous lab where you set an IP address on a switch, you can set an IP address on a router. In fact, you probably are going to end up setting more than one IP address on a router. Each interface on the router that is attached to a different network needs to have an IP address on it that belongs to that network that's plugged into the interface. So the actual configuration process is pretty straightforward. You're going to be in configuration mode on the router, and you're going to go in. So here we are in configuration mode on the router, and then you're going to type interface space and the name of the interface. Like in this case, if we want to set the IP address on this interface right here, we type interface gigabit Ethernet 00, and then we type, you'll see that the config changed to config-if for configure interface. Then we can set IP space address space and what we want the IP address to be. So 192.168.10. And you'll see right here it says 1. So we know that that interface is 10.1. So we put 10.1, and then up here it says /24. That tells us what the subnet mask is supposed to be. We'll learn more about that in chapters 7 and 8. But so we type in our subnet mask 255.255.255.0 and press enter. If we want, we can enter a description in. That's just something so we can read. So if we're looking at the router remotely, we can remember what the router is connected to. And then kind of a big thing on routers, you always need to run this command that says no shutdown. So no space shutdown tells the router to turn on the interface. You won't get any lights on the router interface, and the interface won't work until you run that no shutdown command on it. So that is how you set up the interface on a router. Okay. On this third figure here, they actually have a interactive activity where you can go ahead and try doing that. So, you can go in. Let's see, my one is not working here, but you should be able to type in here and you should be able to go configure terminal and hit enter, and then actually set up the interface like this. Okay, so you should be able to practice with that activity. The other place that you can practice if you want to try setting up some of these interfaces and putting IP addresses on them and so on is you can use Packet Tracer, right? So you should have already downloaded the Packet Tracer software. If you haven't done that yet at home, you're going to want that because there are going to be some things in some of the exams, the chapter exams, where it asks you to do some configuration stuff, and you need to have Packet Tracer on your computer where you're taking the exam in order to do that. So the Cisco Packet Tracer software, which you can download from the Cisco NetSpace website, when you launch it and you log in, it will look like this. And you can go here and you can see that they've got routers, they've got switches, etc. And you can take things like this Cisco 1941 router here, drag it out onto the screen, and then if you click on it, now that's got to be because of the recording software that I'm running on here, because that's should work. I don't know if I'm going to be able to show this to you. Yeah, because when I click on them, they just go away. You'll have to trust me, though. If you drag one of these routers, like the 1941 out on here, and then you click on the router, you can actually go in and go into the CLI tab, and you can configure that router just like you could with the physical routers in class. Now, they don't respond exactly the same way all the time, but it will give you a good way to practice without having a whole stack of lab routers and equipment at home. So you can do that. Also, you can put PCs out here, and you can attach the PCs on the connections tab. You can get Ethernet cables and console cables and so on, and you can connect those routers and PCs together, and then actually build a little network where you can actually do some testing. So you can't do everything from all of the labs in Packet Tracer, but you can do a lot of it. So it's a good utility and way to experiment with some of the functionality that we have with the lab equipment. So I think that pretty much wraps up the highlights for Chapter 6. As always, there's a lot more information in the chapter, so make sure you have read through the entire chapter and ask any questions that you have about the information from the chapter. We'll see you again soon for Chapter 7, where we'll dive into more detail about IP addressing and how we address IP networks.